Good. Okay. Well, awesome. Thanks for coming, everybody. I have a really cool chapter this time around. Honestly, I thought this was one of the more fascinating ones. See if I can get rid of this. Oh, okay, cool. Awesome. So yeah, I thought that this particular chapter was very interesting. This is dimensionality reduction with PCA or principal component analysis. Okay, that. So the idea that the book gave for what PCA is that it's a linear method for dimensionality reduction. This might look familiar to people who have worked with autoencoders before, but basically it just tries to take an original data set or an original matrix of, data, observations, etc., and compress that into a smaller dimensional space. Um, PCA basically just does that via this equation here, where we take this orthonormal basis, or ONB, and multiply it by the original data points to get this encoded representation, basically. Um, the principal this orthonormal basis defines the principal subspace in this case. So the idea is that in the chapter, it gave two kind of examples about what is actually going on. It gave examples as to why PCA maximizes the variance in this compressed form and how it also minimizes the reconstruction loss. Because if you can imagine, like, in order for the compression to be as good as possible, you want the variance of that compressed format to kind of match the original as much as possible. So they go over why this approach maximizes the variance within this framework and why it also minimizes the reconstruction loss. Um, so I don't know if the remote people can hear. There's elephant noises coming from the other room. Um, but yeah, so maximizing the variance basically is the first example that they go through, and I mean they gave a nice little description of that, visual description of that here, where you can see that it's these data points are projected in as far of a space as possible. So for the first coordinate, right, if you'll remember from the last equation, um, every z coordinate is, basically an x coordinate in a different coordinate system. Then the variance of that, those z coordinates is just, the mean of each coordinate squared. So basically, that means that if you want to say get like the covariance of that, you could substitute, or you can substitute this z with b1 of xn to get it in that coordinate system. And so you can do a little bit of substitution because if you're squaring it, that basically, b t transpose times x transpose b, that's basically what you do when you square it. So, and because matrix multiplication like this is commutative, you can actually take this part out, and this is equivalent to the covariance matrix.
Sorry, just to be super brief. It's not commutative in general, but here they define it as one dimensional. And so in one dimensional case.
Yes. Okay, yes, you're right. In the one dimensional case, it's commutative. It's not commutative in higher dimensions because the dimensions might not line up. Yeah, my bad. You're right about that. In this case, it's commutative. So you can actually take it out. And this simplifies to the covariance matrix. So we're left with the variance being equal to the basis vector times the covariance matrix and times the basis vector again. That means that the covariance is similar to the variance because it's goes through this process twice. So if we try and say rewrite this as an optimization problem in order to maximize this here, it says we want to maximize this value and then we subject it to this constraint. And so if you'll remember from talk that Ryan did, which I believe was chapter 7, if I'm not mistaken, we can add this to a Lagrangian optimization problem, with this being the adding this Lagrange multiplier here with the constraint, and then taking the partial derivative of both of these. Basically, because we're taking the partial derivative, we can then set each partial derivative equal to 0 to find the basically the inflection point, or the local maxima where the function stops changing. So when we do that, right, and we set that equal to 0, we're left with this equation. So when at the maximum variance, SB equals this Lagrange scalar times V. And if you'll remember, then this is actually the exact same equation that defines what an eigenvalue and an eigenvector is, right? It's basically this matrix of vectors that are invariant from the transformation, and are equivalent to each eigenvalue times, the original matrix times the eigenvector, and then the eigenvalue times that eigenvector. So what this basically says is that the optimal at the maximum variance of the basis vectors are actually the eigenvectors of the matrix or data itself. Anyways, that's construction noises. So from the maximum variance perspective, we get eigenvectors, essentially, for this basis vectors of the transformation. The other way that they looked at it was like projecting it and trying to minimize the distance between data points and their projection. Basically looking at this side instead of at this side. Now, this part involved a lot of math, so I put the equations here. I'm going to kind of try and do my best to like reason through what the intuitions behind these things are. But there is a lot of like equations that they put out. So the way that I see this is we basically define this distance metric because we want to minimize this, essentially, the distance between X and its projection. Now we're basically doing the same thing. We're getting like, the partial derivative of J equal to Z. And then we're basically left with, stuff like this, et cetera, et cetera. We set this equal to 0, et cetera. We're left with pretty much the same thing from the maximum variance perspective. We're left with each Z value is X times this basis vector. And so they get the coordinates first. So now we just need to figure out what this basis is. So one identity that they use to kind of solve this is that we actually can expect each of these vectors, these projection vectors, to be orthogonal. That is the smallest distance. And you can kind of see that if you're just like looking at it graphically, you can see that the shortest distance between a point and a line intersects it at a right angle. I think there's even like a Euclidean, that's a Euclidean something. It's been known for thousands of years. You can look at it, but they just had to write a whole bunch of math about it anyways. So basically, they leverage the fact that this is a basis vector. So each coordinate in that basis is just a sum of those, each basis vector multiplied by it. So they leverage that here. They substituted in XB. They basically did all this other stuff. They found that you could take this out. I'm sorry. They got the projection and the original data point. They put that in these terms, and you can actually subtract one of them from another one, right? And then you're left with this projection matrix.
which is the orthogonal complement. And they proved that it's orthogonal. I don't know why I wrote orthonormal. I forget if it's actually orthonormal, but that it's orthogonal. They proved it by this identity that we talked about, like in like chapter 3 or something like that. So pretty much like a mathematical way to say something that you can like just see with your eyes. So, but now that we have this projection matrix, right, that this like this basis vector squared essentially, b times itself transposed, is the projection of x onto, this optimal sort of, projection here. We can actually take out, we can put x, the projection of x, in terms of x. So we can substitute it with, this basis squared, and then work with that. And so they do a bunch of math here. I'm honestly not going to go through all this math. It's a lot, and I don't like. I looked at it for like quite some time, and there are a couple of things that I think that is interesting, that I found to be interesting. One, I think that it's interesting that we can actually get this covariance matrix from this equation because we can express the projection of x in terms of x. So I think that that's interesting, that that is pretty much why we can find in the math this, this S here, this covariance. And if you kind of think about it from like a, picture perspective or a graphical perspective, right? Basically, like the distance, it should make sense that the optimal distance between the data points is proportional to the size of the covariance matrix. Because the covariance matrix is just an average distance across each of the features, right? It's like a sum divided by the number. So it should make sense that the distance, total distance between each of the data points and this line or subdimensional space is proportional to that. And then we also have like, the basis vectors themselves as well. And then honestly, I don't know why they can put trace in here. I don't know if anyone understands why this is an identity. I don't get it. But basically we get the same thing. Trace of, and this is the same exact step essentially that we got for maximizing variance, right? So they mean the same thing. The distance, because the optimal projection is orthogonal, because it, is a right angle. So we can continue these derivations from here. The only other cool thing is that, because each of the basis vectors are an eigenvector, the distance is an eigenvalue, or is, a sum of eigenvalues. Which also makes sense if you think about it super hard. I'm not going to go into why, because that means I need to think about it super hard. But like just to say that these two things are equivalent. So oh, for some reason these two slides got flipped up at some point. So sorry about that. So I just want to take a step back and summarize basically like what this means, because that's kind of in the weeds. But what this basically means is that the optimal projection, linear projection with a single term of a larger dimensional space into a smaller dimensional space, just using linear transformation, are eigenvectors of the correlation matrix, S. So what that means, if you'll remember that what eigenvectors are the vectors given a certain linear transformation that remain the same in the same direction under that transformation. So they represent kind of the constituent parts, or that which remains invariant. So you can increase, like different dimensions of that, and it'll remain in the same direction. right? So the eigenvectors of that are the first M principal components. That pretty much describes the largest, and if you start with the largest eigenvalues, right? The most prominent eigenvectors, you are basically describing the majority of variance in that data set, the first M number of times. And we use that as the basis for that encoding, that optimal projection onto that subspace. And so that new subspace, the principal subspace, is created, and principal components and the data points are projected from the original set using the linear transformation Z equals B transpose X. Now also keep in mind, this is a linear transformation. So this is a simple linear transformation. In actuality, like, if this could have an activation function, and what happens if oops, come on. And then what happens if you want to add a bias? It becomes an affine transformation. You add plus B or something, plus whatever you want to call it, like there comes an affine transformation. This is just a simple, I kind of think about this sort of like linear regression in its simplicity almost. But it's like an encoder. It's a very simple encoder. Minimizes Euclidean distance, maximizes variance. So with that in mind, I'd like to open that up to kind of some questions, discussion. Did anyone have any questions regarding this?
So why are we maximizing variance? I thought we want to minimize variance.
Right. So if you can imagine, and that's a good question. If I don't know if people heard that, why are we maximizing variance instead of minimizing variance? And if you think about it, right? So if you were to minimize variance, like the spread of the data in like a projection, right? Probably get it down to like a point. And so you basically like lose all the information of the data set itself, So we want to maximize that because we want to describe, the nuances of the data or the variance of that data, Does that make sense?
Yeah, so we're maximizing the variance of the data points, not the
Of the projection.
projection.
Yeah, of the encoding. So like
If you swap the verb preserve instead of maximize, then it might be a little more intuitive.
Okay.
Yeah. That's actually really good point. Yeah, preserve the maximum.
It is maximized, but it's
Yes, yeah.
you think about there already is variance. You just want to preserve it.
And the variance we're talking about, it's the data point in relation to the eigenvector, or
No, it's just inherent in the measurements of your data.
It's the relation of the data to itself. So the thing that we're focusing on in order to maximize the variance is the covariance. I forget if it's covariance or correlation matrix.
Covariance.
Thank you. Yeah, it's a covariance matrix of X times itself. And then you divide that by the number of data points you have. So it's like the mean how all the data points relate to each other, right? The reason that we take an eigenvector of that is because that basically, or eigenvectors, is because that like captures the majority of that information, the largest pieces of that variance, that information. And then we use that to project the data onto a lower dimensional subspace.
Eigenvectors according to the direction of the times points. Eigenvalues basically variable of the price points.
So we think of it in terms of a swarm of data points space, in free space. If imagine a Gaussian distribution along a swarm of points, it's going to have you're looking for a an ellipsoid. And you're looking for the pixel axis, the ellipsoid. Okay.
So that's not immediate best.
And then you can use that to use the dimensionality.
Okay.
That's how I understand.
So in regards to what you're saying, so this eigenvector is the vector that best represents the data, not like the
Actually,
of the data.
they used an ellipsoid in one of the pictures. I didn't put it up, but Oh, actually, wait, hold on. Yes. Okay. Actually, this. I'm sorry, it's in black and white here. Yeah. So, this is also, uh, this is like kind of like the ellipsoid, more or less, that you're talking about. So, and I'm bouncing forward a little bit here. So,
Yes, before you get to the how to compute it,
Yes.
can I jump in a little bit about
Yeah.
if I could ride on your coattails, um, imagine that you had a diagonal covariance matrix. Okay. So then basically, you have an ellipsoid that is aligned with your, um, um, I keep blanking, but aligned with your axis. Okay. So if we're just doing two-dimensional, then it means that the ellipse is either horizontal or vertical. It's not diagonal. Okay. Um, So then basically what's going to happen there is that the maximum spread is going to be on the major axis of that ellipsoid. Okay. And the eigen, so this is your covariance matrix. And so your covariance matrix describes the spread of your data. All right. And so if the maximum values are along, say, the x-axis, okay, then you know that the x-axis has the maximum distribution. And in fact, you can do a little bit of math and you can see that the eigenvalue associated is going to be proportional to the length of the major axis. And that the second eigenvalue is going to be proportional to the height of the minor axis. Okay. Now there's a theorem that says if you take a vector space and you rotate it about the origin, the eigenvalues don't change. So if you combine those two, then you no longer need a diagonal covariance matrix. For any covariance matrix, even if the data is distributed on some angle, it will always be true that you can kind of draw an ellipse around it. It's two dimensions, it's multiple dimensions ellipsoid, right? And the largest axis, the largest major axis, will correspond to your largest absolute value eigenvalue. And so you can go on and so forth. And so this is how you have the intuition that since the covariance matrix represents the spread of your data, then whichever is the widest, that is then what corresponds with your eigenvalue. So for me, it's easier to think about it starting with a diagonal covariance matrix. Then the calculations are very simple because, right, the upper left corner is just the variance in the x direction.
Yeah.
And the second diagonal is just the variance in the y, and then the z, and so on and so forth.
Yeah. And the covariance matrix, because it's x by x, it should be triangular anyways. So like like a diagonal matrix has all the rest of it zeros. And so it's like, that's,
yeah. And so then just one more intuition. So let's say you had two eigenvalues that were 5 and 3. Okay. So I've got a spread of 5 in the x direction and 3 in the y direction. Can I beat 5 by going on the diagonal, by going in between the two? Okay. And every vector is represented by a sum of its spaces, can be represented as a sum of its basis vectors. Okay. And so if you use some fraction less than 1 of the 5 direction and some fraction less than 1 of the 3 direction, you're never gonna get a number bigger than 5. You can get any number between 3 and 5, but the smallest you can get is 3, and the biggest you can get is 5. And so if 5 is the biggest, that's why you're going to use that. You never use an in between. So you need to know that 5 is the biggest, and also that you can't do better. Because hypothetically, you could say, well, what if I go a little bit of this one, a little bit of that one? Maybe it's bigger. But think about it intuitively. In a 2D ellipse, you're never going to get farther away from the center than along the major axis. You can get any amount in between, but you can never get farther away.
And I'm pretty sure, correct me if I'm wrong, but I think if you were to add like maybe some of the largest eigenvalue, the first basis, and then like some of the next one, I don't think that would be an orthogonal projection. So it wouldn't be the direction that maximizes the variance of the projection. So you'd be losing some information.
Yes, that's right.
Yes.
Yes. But my argument about in between was assuming there are orthogonal bases.
Yes. Yeah.
Perfect.
Okay. So, and for some reason, I think I must have put this like before, on accident. So my bad for that. But, it went through a couple of different methods to like compute PCA. So really all you have to do is compute the eigenvectors of this covariance matrix, essentially. And so we did some eigenvector, calculations. I think it was like chapter 4 or something like that. So it's pretty similar. So like since S is a square matrix, you can actually just use eigendecomposition. You can also use SVD, right, which was chapter 6. Okay. And basically you can just get the U. Now in this book, they list their X as like D by N. And they do mention that that's kind of weird. You're typically gonna, when you get tabular data, you're gonna have it like N by D, number of data points, and then D dimensions, etc. But they do it in like the reverse order. I think if you were to take an SVD of like data that you would find in the wild, it would actually probably be more concerned with the V. So remember that U is the represents the relationship of the eigenvectors of the codomain, and V represents the eigenvectors of the domain. And you are interested in the codomain because you're interested in D features, right? So these are just the eigenvectors. You can just literally take the first, M, vectors of this, and then just use it as like the basis here. Now, one quote that I thought was really cool from the book is like the relationship between the eigenvalues of S and the singular values of X provide the connection between the maximum variance view and the singular value decomposition. And like, listen, the first time I read that, it made like complete and perfect sense. And the second time I read that, I lost it. So I'm serious. And I'm kind of mad about it because it was like super profound. So does anyone want to maybe elaborate on this like a little bit? Does anybody like want to think about that for maybe a second and comment?
I was actually confused by that myself. I trust it, but I don't have a great intuition. It's clear to me that U is a orthogonal basis, and if you want to, scale it, then you can make it as orthonormal as well. But I haven't quite wrapped my head around that the two are tightly related. And the thing is, it's not true that the eigenvalues of X are the same as the eigenvalues of S, the covariance matrix. Okay? The eigenvalues of X are the square roots of all of the eigenvalues of S. So there's no direct, there's a relationship, but there's not an equality or equivalence in that sense. So it's like, there's enough there that I feel like it's not. I don't disbelieve when somebody says that that's true. I just don't have the connection.
I swear it hit me like a ton of bricks too. It was like super profound, and I just can't wrap my head around it anymore. All right, well, I don't know. It might come to me later. If it comes to anyone later, feel free to put it in the chat. Let me know.
I actually asked ChatGPT, and ChatGPT said that most of the time people do not do what they say in the chapter for the 90% of the chapter, which is calculate the eigenvalues and eigenvectors of the covariance matrix. Almost everybody uses the singular value decomposition. So even though they like mentioned this for not very long in the chapter, like a page or two, this is the way, this is the primary way. And I think it has to do with, again, it's just computational efficiency
Hey
and
Ted,
also numerical.
sorry, I hate to interrupt you. Can you see my video?
No, I think you're still just sharing the slides.
Oh no, but am I in the chat or the thing still? Because I think my Zoom is frozen.
Oh, I don't know if it's changing, but oh yeah, your video is, sorry, you mean your screen share, yeah.
Okay.
You're still holding your cup.
Wait, can you hear me?
Yeah, I'm getting your audio actually.
You're getting my
I
audio?
didn't realize, that's why I didn't realize.
But my video is
Unfortunately, yes. You just do not have good,
no, this is because I tried to put Arch Linux on this, and that's now it's this. Yep, I messed around and I found out.
if your computer's responsive, you might want to just try disconnecting and reconnecting.
Um, you know, yeah, okay, I'm gonna reconnect here real quick.
All right. So while you're doing that, I was going to do this at the end, but I'll just do a second detour here. So every time PCA comes up, I bring this up.
Ted, I think you're muted. I cannot hear you.
All right. Sorry, I was using Liam's microphone, and sorry for you guys online, you didn't hear anything after Liam left. So super short version. Are you back in now, Liam?
Yes.
Yeah, you're still muted in the Zoom. All right, so if you turn down your volume for a sec. All right. So you can't turn down your volume? Okay. Okay. Windows down. All right. How's it? Okay. All right. So for those of you online, I'm going to give you a super short version. But if you do dimension reduction on a traditional, say, tabular thing, 25 dimensions, reduce it to 5, and you've preserved whatever arbitrary definition, a lot of the variance, 90%, 95%, or whatever. Is there any kind of guarantee that you will have like 90% as accurate of a model as if you did the full model on the full 25 dimensions? Are you going to guarantee to get 90% or square root of that, or 81% or 95 or whatever? Is there any kind of guarantee that you will get a minimum quality model after you've done dimensionality reduction? So again, I'm saying that there clearly is a lower dimensional manifold that so you've preserved a lot of your variance.
sometimes used as a denoising of the data. So, and usually the noise data is in this lower lower PCA. The PCA that describes the less variance in the data. So it could probably have the same performance, or it could generalize better, because if we train a model on the whole data, and especially that we have 25 columns, we don't know how many samples we have. We always, when we use some machine learning, we have risk of overfitting. And if we, let's say, denoise the data with PCA and then run our model on denoised data, then the risk of overfitting is less.
Yeah. Okay. So comment. PCA is sometimes used for denoising, so you can get as good a model and sometimes even a better model after you use PCA. Okay, that's fair. My question though is, do you have guarantees? If you use PCA, might you wind up with a worse model? Is really the bottom line of what I'm asking. Okay.
So there is no guarantee.
Okay, so you could have nonlinear dependencies. Any other comments?
I think PCA also kills the sparse vectors. If there are sparse features in the matrix, then you will lose those too.
Okay, so I don't know if you guys online could hear. So there's a comment that, like, in a neural network, the transformations are nonlinear, they're very complex, there's no guarantee. I think somebody online was also speaking at the same time. I wasn't quite able to hear.
Yeah, I can repeat. So if you have a
Yes.
sparse feature, and if it is an important feature, let's say relevant to your label, the sparse features usually they disappear, or they in that condensation process. So you lose most of the information, almost all the information, and then you also lose that important feature, if it makes sense.
Okay, so to short summarize, you said if you have sparse features, you could lose that information. What do you mean by sparse?
So let's say mostly zeros, and yeah, mostly zeros.
Okay, mostly zeros. Yeah, I think you've got the gist, but it doesn't necessarily have to be zeros. Okay, so the bottom line is that the signal you're looking for might not be in the directions of maximum variance. Okay, I think the example that I gave right here in SDML, like whatever, 6 years ago when we first talked about PCA. All right, can you mute?
Oh, okay, gotcha.
Is imagine you have like basketball players and you have something like height and some measure of their reflexes, how fast their reflexes are. Okay, there may be this massive correlation between the 7 foot tall people have slower reflexes and the little fast guards that are only like 5'10" or whatever have much faster reflexes. But what you actually care about isn't this main signal that tall people have slower reflexes. What you care about is how their reflexes compare to other people of the same height. And so that main direction is, if you preserve that variance, what you will preserve is this concept that tall people have worse reflexes. But what you really wanted to do in terms of predicting if somebody's a good basketball player is, but are you unusual for your size? Possible. Okay, I'm not saying that that's necessarily the only definition of what makes it good, but you could see how perhaps that the principal component is just going to give you that main signal, and that's actually not the pattern that you're trying to model. So the key thing is just knowing. I don't think if you're doing deep learning, people don't tend to use PCA, but I just wanted to kind of share that there is no guarantee with PCA. So as, sorry, I think it was Hakan online said, you can lose exactly the features that you want just because they are not as high variance as the features that are high variance, but you just don't care about, right? So just imagine I had a data set and I could get 99.9% accuracy, and I just added 10 features that have no relationship whatsoever to my problem after I've already solved it, but have very high variance. Now, if you reduced it to 10 dimensions, you're going to lose every feature that you ever used to have, and you're just going to keep these 10 nonsense features I just added. So that's my sort of adversarial way of showing you that you could fake out PCA.
You know, I have a thought about that.
All right, you want to try unmuting and I'll mute.
So I have a thought about that, and I'm not entirely sure. So, but I'll bring up that thought like when we get to probabilistic PCA. For now, I'm just gonna go through like kind of in chronological order. So we did talk about we can use SVD, calculate that. We can also use low rank approximations. So you really are looking for a low rank approximation of this this eigenspace or principal subspace of the covariance matrix. So basically, you could just do a low rank approximation, and that way you'd only have to do it like a number of times. This is power iteration. It gets you the first eigenvector, the most prominent one. And apparently they use this in Google PageRank. So you just like take some random vector, and then you like modify it, or you try and is it minimize or maximize? I think you minimized. Well, this one kind of makes sense because you're minimizing that. You're minimizing how much this changes. And that should make sense because you're looking for the vector that doesn't change under this transformation. So you want that to minimize, right? And then they also gave this one trick for high dimensional data, like such as images and stuff like that. Computing the eigenvalues or the eigenvectors is a computationally complex process. I think they said it was like cubic or something. So instead of having like, D by D, if that's like 135 by 135 or something like that, you could actually probably flip it into an n by n matrix where n is the number of samples, and they did this in a kind of a tricky way so we have this equation that we saw before, right? They just multiplied X transpose on both sides. And so instead of this, but that changes your basis vectors, right? And they made X transpose B into this CM. So then you basically have to get the eigenvalues of X transpose X, which is n by n. It might be easier for you to do. And then, basically undo this operation, recover XCM as the eigenvectors of S. So that was a nice little tricky thing. I'm sure they do that under the hood in some stuff, or maybe they use something a little bit more elegant. I'm not entirely sure. The last time when I did the eigenvector thing, I used QR decomposition. I think that's how they do it under the hood now. I don't know if they do it at scale, but it seemed pretty, I think it was like n log n, something like that. I don't know. I thought it was pretty good, but that'll work too, definitely. So just and then the steps, right? So earlier we were talking about this ellipse. So imagine you have this original data set, which you can kind of see kind of is distributed in an ellipse. I bet under the hood, in order to make this graph, they might have done something with an ellipse. I don't know. It kind of looks suspicious to me. So you have this original data set. First, you want to get it to where mean is 0, just so you don't have to, it's a linear transformation, not an affine transformation. So you just subtract the mean from all the data points. And then you want to standardize it. So you divide all the data points by the standard deviation to make sure that it's, again, you're not scaling anything unnecessarily, which causes numerical instability. Then you get the eigenvectors of this covariance matrix. And as we mentioned, right, because this is basically an ellipse, your most prominent eigenvectors can kind of be in this direction, and the other one's gonna be in this direction, right? And this pretty much has like two directions, more or less. So let's say we want to project it in one direction. So we want to project it onto this line. So we take the first eigenvector, most prominent eigenvector, and we basically just project all these data points onto this line. And then you undo the standardization and move the data back to, where it was. And basically then you have a compressed representation. Now this is one dimension, so it's not going to be like incredibly good for this data, but this is just like, an example. That's basically what it looks like. So you can kind of see that here, right? I think they said this was like a 256, 125 by 125 image, something like that. As you can see, if you try and reconstruct the data from its projection, you can kind of eventually get pretty close to the original, or get something kind of like it, and that's kind of the idea of an encoder and then a decoder, is you're trying to get, uh, the data that you originally put in. So, yeah. So I think we kind of talked about like sort of this from an intuitive perspective. So I'm just gonna, I'll go on.
Liam,
Yes.
comment. So if you go back, for step C, where you divide by the standard deviation and make the variance 1 along each axis, I had to actually pause for a second, because then I'm like, oh wait, haven't we just lost all the variance information that we're now trying to preserve? But as you can see from that diagram in the upper right corner, it does have variance 1 in the x direction. It has variance 1 in the y direction, but we haven't lost the information about the data. As you can see, it's still got the spread of the diagonal. And so, but I had to think for a moment there. It's like,
I have a question for figures B and figure C. It just doesn't seem intuitive for me that when it's dividing the data by the standard deviation, that it somehow rotates. Does it? I mean,
when you
do
divide
have
by
some
the standard
iteration?
deviation, it doesn't rotate, it scales.
All right. Well, for me, it seems like it is related a little bit.
Yeah. So I think that's,
Because, and even if we go, I'm sorry for interrupting, and if we go from like figure E and then from figure E to figure F, then you see that it's like this rotation, and we are not talking about this rotation here. I mean, I'm not an expert in PCA. I'm just like, this is what drew my attention. I was like,
In 2D, it's hard to tell the difference, okay? But they are not rotating those points. They are scaling them coordinate wise along each axis,
okay.
which is a different transformation than a rotation.
You can think of it as compressing the axes, and you're not actually doing anything to the data, you're just like making the axes denser. For example, the x-axis, 1/2 just compressing the axes together. Same thing with the y-axis, it's like normalization.
Yeah, so if you couldn't hear online, the comment was just stretching or squishing each axis separately, successively, one after the other. You could do them in parallel, but you could think of them all. It would work fine if you just did them iteratively, separately. And so,
Yeah, I think it just the sizes of the pictures
Yeah.
B and picture C a little bit different. That's why I was a little bit confused because I didn't see any rotation here.
No,
of, like as a visualization, just
Yeah.
seemed to me a little bit.
couldn't really swear to it, but if you had two points on the scatter plot that were at the same horizontal height or whatever, the same height or whatever. If it were a rotation, then they would actually no longer be the same height, but if it's just scaling along the axis, it'll stay the same. And so if I squint and I look at some points that seem to be the same height, the same width, then it does look like they stay the same from B to C, and then they don't change rotation slightly. But Yeah, I agree. It's hard to tell just from this small position.
And I would say I think it looks like it's rotating because the variance is greater in the x direction than it is in the y direction. Like it's between like I don't know, it doesn't really give a clear thing for like the left boundary, but it's like it goes up to like 5. So if you like so the variance in that direction is like more, so if you divide it by it, then it kind of like, you know, kind of looks like that a little bit. I don't know. Any other questions regarding like, this these steps or like anything like this? Okay. All right. Moving on then. So probabilistic PPCA is I have never heard of this and I think it's pretty cool. So the comment that I was wanting to kind of think about earlier. So I'm going to go through this really quick, or not really quick, but first, basically, we consider, if you'll remember, like I think it was chapter 8, we talked about latent variables in a probabilistic sense. We basically consider the encodings, or we consider this encoding Z to be a latent variable, more or less. A projection into this subspace that contributes to the overall variance technically is a latent variable. Very simple sort of situation. And so then we can kind of like see it as a probability distribution. So we assume that if we wanted to turn this into like a generative process, probabilistic model, we could say that, we add the mean, which is like kind of one of the steps that we did earlier. And then we add this epsilon term, which is just what we consider to be the Gaussian noise, and actually that's what I wanted to say. I was kind of curious if you have like the first number of eigenvalues and you find the variance past that in like d minus m, right? That last, if you find that that is Gaussian, or that's, generally Gaussian, there probably isn't, much useful information in that, amount, or maybe PCA will do a good job or something of that nature. But yeah, that was just my comment there. I'm actually not sure. Yeah, so in the book, they assume that Z is normally distributed, or we assume that Z is normally distributed. We assume a normal distribution. So this probability of X given Z, the data given the latent variables and these basis vectors and mean and standard deviation, we can turn it into a Gaussian distribution of this conditional distribution. And then the standard deviation be standard deviation times I. I'm kind of like, a part of me gets why that's the case, but like I can't really articulate why that's the case at the moment, but it's in the book. So we basically interpret this as like a Gaussian distribution. And so they provided a nice little chart here, which, X is, or Z is conditionally dependent on Xn. And so is these basis vectors, as well as the mean and the standard deviation, something like that. So when we put it like a probability distribution, like we tried to optimize this earlier using a Lagrangian, but now probabilities, chapter 6, we can actually use maximum a posteriori map and maximum likelihood estimation to get either a point estimate or an estimate of like the correct probability distribution. Because we can now get a likelihood. We can turn that into an integral, assuming that Z is normally distributed. And then we could just like kind of solve that. And then, put in different data points and get different results. We can basically, treat it like a probability distribution. So as you can see here, right, using PPCA, they digits near the center that look, that follow the, the main trends of the data when they're reconstructed from this probability distribution, they look pretty good. This one's a little bit dubious, but then again, it's out here, so I don't know why you would do that anyways. So, but like most of these are like, they're decent, but the farther away that they go, the more they start to kind of deviate. They're not described correctly, because there is some loss. You're missing information, etc. And I didn't actually put this on here, but they did give a particular way to measure the how much information is lost. And I wish I had added that, but I did not. So it's like C of M. Definitely feel free to skim over. It's around this section. I'm sorry I didn't put it in here, but yeah. So from a probabilistic point of view, this is kind of what we're looking at. Are there any questions pertaining to this kind of like probabilistic outlook?
So what are the different scenarios? Obviously, I got a chance to figure out that. What are the different scenarios where probabilistic and statistical surveillance?
Well, I would say, because I actually haven't used probabilistic PCA before, but I would say, like, in situations where you want to generate new data, or you want to make like, what you can get from this is like, hey, this particular data point is like out here, it's anomalous, or it's like, it's within like 95th percentile of something, and you can get like a distribution, and do stuff with that, as opposed to like a point estimate. You know what I mean? That's kind of how I see it. And then if you just use PCA, right? Yeah, point estimate as opposed to like general like probability distribution. You can treat it, you can do all sorts of stuff with it. That's kind of how I see it.
Can I follow up on that?
Yeah.
Yeah. So I think you pretty much nailed it. The two main reasons why you use any probabilistic model, whether it be PPCA or be anything else, it's either because you want a generative process, or it's because you want an understanding of the potential variation around your point estimate. Okay, so you can do a full Bayesian method, and then basically the mean will be your map estimate, your point estimate, but you'll also know how much uncertainty you have around that. So if you remember last chapter when we're doing a linear regression, you would see sometimes you have very small, I don't know the right technical term, I'm just going to say standard deviation, but I think that's the wrong word. You have very small standard deviation around your point estimate when you're near the training data points. And in particular, when you get to the extrapolation zone, far to the left, far to the right of anything that is in your training data, now the variance balloons massively. And so that would be useful for certain things if you wanted to know whether the model gave you a prediction. It said, hey, I predict 7, but should you have confidence that it's really 7, or is there a lot of risk and nothing? Basically, the way I see, I'm not sure if I got this right, but the way I look at this probabilistic PCA, if you look at a variational autoencoder on images, basically what you do is you run a CNN that does a very nonlinear transform into its embedding, and then they just do probabilistic PCA on the embedding. It's then a linear transform to a latency, and you've now turned a CNN, which is not a generative process. Okay. One mapping can only give you, in one direction, a single embedding, and an embedding can only give you a single image. If you were to find a way to reverse it, right? But now, when we go and turn this into a probabilistic thing, now we can actually sample from that latency that for convenience, most of the time people model it just as a multivariate state. So if your original distribution was not unimodal, what you need is that complex nonlinear transformation to turn it from a multimodal distribution into a unimodal distribution, because that's the only family of speeds that get parameterized in this multivariate class.
Makes sense.
Thank you.
Of course. And I have two more slides just about like some of like, further reading some of the like not too far gone, but like some of the further reading stuff. But before I, go on to those, do we have any other questions regarding like, the main body of the chapter? Okay. So I just actually wanted to give kind of like, so they mentioned in the further reading, and don't hate me, this is actually a little bit off book, so I'm sorry about that. But like, just a little bit. The they mentioned that this was like an autoencoder. I see this as kind of being the simplest autoencoder, personally, like the simplest that you could possibly have. You are assuming that what you really care about is the average relationship between all the data points and themselves, the average, like the covariance, just an average, and that's pretty much like what you want to model. And you want to, either reduce the size of your data to that with that in mind, or you want to generate data from that. Obviously, this is assuming that your data is nice and behaves well. And in practice, a lot of times it doesn't. And so like one of the techniques like this is like literally Z equals BX, but there's a lot of like deep learning solutions that you just put in there instead. And you can, linear, nonlinear, in this case, like a variational autoencoder. If you'll remember the section where, talked about sufficient statistics, it tries to basically predict the mean and then the variance. And then it uses that as this encoding in this encoding. Oops. Okay. And so just to put it out there that like, this is like a dense layer. This is a dense layer. There's a dense layer at the beginning. There's a dense layer at the end. I think in this particular solution, it's like 256. This entire solution is honestly like, I encourage if people haven't used this before or are interested in like, seeing a good example of it. This is like a page of code, honestly. And it's really not that bad. They use TensorFlow and stuff. But just to say that this like, this simple linear function can become more complex and also nonlinear. And one of the things they mention in the book actually is that if you were to turn all of the activation functions into just the identity matrix, then you basically have PCA, except with a couple of extra steps. It's like how like linear regression turns into a neural network. This is like, very, very simple. So, and you can see like, so when we're training this, right, we're training X on one side and itself on the other side, and we're having it guess itself. And although we were able to directly maximize the objective function, earlier for PCA, for this, you would need to train it using that objective function. And here they just use mean squared error. But if we remember, what you're actually doing when you're minimizing Euclidean distance is you're actually maximizing variance. You're maximizing the amount of encoding that you are storing in this late representation, this lower dimensional representation. And then you can get like, it's like these digits look a lot better. You know what I mean? Like, I don't know, they look a lot better than the PCA. And with larger data sets, with more complex relationships, you most certainly might want something more complicated. And there's a lot of different, as we might know, there's a lot of so many different ways to do this, but you know. And then I also went into a little bit further detail on one of the things they mentioned in the further reading, um, which uses kind of like PCA, but is sort of um, a little bit. Actually, you know what? First, before does anyone have any questions or anything to add or comment about this? Because I know a lot of us have, you know, used this sort of process. Is there any, and not just variational audio encoders, but just auto encoders in general? Is there anything anyone else would like to ask or comments about this? Okay, I'll move on. All right. So one of the other things, I didn't get into all the further reading stuff. There's like factor analysis that I thought sounded pretty cool. And then they used like, there was like a Gaussian thing, GV, something like that. Like they all sounded pretty cool, but I just like, I just went into this because I was curious. This is kind of where PCA is sort of assuming some degree of Gaussianity. ICA is like kind of the equivalent of you have multiple conversations in a room and you want to pick out what those conversations are. So it's kind of the reverse, you know. Basically, as a pre-processing step, they use PCA, but then they want to determine the signals that are the least Gaussian, that are like the least noise-like. So basically, like you have this X equals ASW. The A is this mixing process, and these are just matrices. And then the W is this unmixing process. And then S are the actual like signals. And you can pretty much do the same thing, I imagine. You could turn it into a probability distribution as well if you want to generate new stuff, you know, or et cetera, analyze it on that capacity. Although you might have to do some math, I guess. But you want to get these like signals. And instead of like maximizing or minimizing distance, maximizing variance, you're actually maximizing metrics of non-Gaussianity into like kurtosis and negentropy. Negentropy. That one. I've used kurtosis before a little bit in finance. It's basically just like the tails of your distribution, and it's a measure of how non-Gaussian it is. So you're basically maximizing how non-Gaussian this is, how strange it is to get these signals. And so I just thought that was kind of an interesting sort of way to look at it, right? So subtract mean, decorrelate, which means you project all this stuff into the PCA principal subspace. That's how they decorrelate it. Scale and normalize, standardize, pretty much. And then you find this unmixing matrix by maximizing that factor in an objective function, same as you did with this. I don't remember if there's an algebraic solution, but I left the link underneath this. Unfortunately, it cut off, or maybe I forgot and I should add it to the chat later. Either way, I think this is a really cool, like, alternative, one of the really cool alternatives. So, yeah. Any closing comments on this? All right. Well, that's all I got. Appreciate it.
Awesome. Thanks, Leon.
Of course.
Could I jump in and just show some cyclic words just related to this?
Yeah.
Yeah. Okay, these ones color might be helpful for it, but we can carry on without. So I wanted to add in like all of this stuff we've talked about. It's important to understand the nuts and bolts, but almost all of these concepts, you go over to scikit-learn, there's an implementation for you, and it also has all of the different solvers and methods and everything. And we didn't really talk about it that much, but sometimes it's like, oh, if you have a lot of samples, it's faster to do it this way, or if you have a lot of features, it's faster to do it that way. And scikit-learn will be good at kind of just picking the best method for you. So that's one of those details that's kind of hidden for you. But there's all these options. So like looking specifically at PCA, there's all these options here. And so if you were to actually just try and compute PCA for some features that you have, you can go look at it and you fit your PCA to your data, and then it will just give you your explained variance ratio. So you can say my first component gives us like in this one, it's showing 99.24% explained variance. So that means that your data can be reduced down to one dimension and it captures a lot of the variation already. So that was related to the variance discussion earlier. And then they also have many different visualizations here just to understand like PCA isn't the only like dimensionality reduction method. And so if you're ever interested in like, I think PCA isn't the best suited for the problem that I'm trying to solve, they have examples of different kind of data sets. So this is kind of an interesting one where they had 64 by 64 images of faces. And then they said, reduce this down to 6 components with a bunch of different methods, and then just see what it recovers back out. So these are the original faces images, and then they do reduction with PCA, and they say, okay, we reduce it, and then we go back to the original data. This is what was preserved out of the information, basically. And this is NMF and fast ICA, so that's related to what Liam was just pointing out. So there's all these different methods. So if you go over here, this section for decomposition, all of these are like kind of your different options that you can have on top of it. And so one of the common ones that people show is this Swiss roll thing. So it's this 3D data that goes in a Swiss roll, and then you can say what happens when I try to reduce this down with all of these different methods. And so this is what PCA looks like. It ends up just this flat map, and you lose a lot of the information because it's just linear and it's just trying to flatten it. And these are various different methods that might be more suited when you have data that looks like that. So when you have data that looks like that, you might have to kind of figure that out for yourself. But just wanted to say like PCA is very common, very typical default, but there's a lot of other options out there. And it's pretty easy to just say like scikit-learn, import something different, and then you get to try different options.
But I'm gonna share my soapbox comment that I do every time dimensionality reduction comes up. So if you think you have linear relationships, use something like PCA. It's faster and it's simpler. If you think you have nonlinear relationships like Swiss roll, then use something else. But if at all possible, do not use TC. That's my soapbox. Because basically, TC has hyperparameters that nobody really understands the hyperparameters. And there have been a number of people who show that basically from any data set, you can create a TC plot that sort of looks like a circle with like what seems like clusters. And so therefore, the fact that you produce such a plot tells you nothing actually about whether or not your original data.
I think it picked up a little bit of it. I don't know if it totally heard, but yeah.
Okay, cool. Well, appreciate it, guys. I think that's about it. It's about all I got. So,
Oh, we actually have a hand raised.
Oh.
So I don't know if you're sharing audio, Liam.
I'm not.
John, why don't you try and then if,
Hold on.
if the
Let
room
me
people don't hear, I'll repeat it.
let me okay, so if you turn your audio off and then I will turn my volume up. Okay. I have to turn it up again. Right. Testing. Okay, can you say something? Oh, okay, I just fixed it.
All right, go ahead, Hakan.
Yeah, thank you. So I wanted to like highlight one thing because I used PCA before in production, and then something that that we need to be careful about. I want to mention here, because when you create the when you use PCA and calculate all those eigenvalues and eigenvectors and do the transformation, and if you keep using that, there was a problem. There was drift in the data, and then the mean and variance of the data was changing, right? And we were still using the old, transformation. So we realized that started hurting us, and then so I wanted to highlight that. So it needs to be updated as you train the model, or it's not just one solution that will apply to everything. So that was learned by experience for me.
Absolutely. Yeah, that's a very, very good point. That if you use PCA on like, a particular data set, and then, the statistics of that data set change over time, you will need to probably monitor that, or, uh, maybe try use a different model, or like monitor that at very least to like make sure that that doesn't happen. So definitely. Is there anyone, actually, is there anything else anyone wants to talk about as far as that goes?
The defense. TC. I'm sorry.
Oh, we have defense of TC.
But it's mostly used for data visualization to see if they, like, let's say you have a data set with different cell types and you want to see if different cell types are clustered together. But like Disney is like more ancient method, let's say. The like currently used method is meetup, which is basically Disney, but you can adjust more hyperparameters. And for example, complexity is one hyperparameter that basically tells you if you want to capture more local variation in the data, let's say not binary stuff, patterns. And that new map, it actually uses the PCA first, like a linear dimensionality reduction, and then use a nonlinear dimensionality reduction. And that's why, because usually the bioinformatics data set are very high dimensional, meaning we might have like 60, 180 features, like columns in the data set, and like if you do like a nonlinear dimensionality reduction on this set, and the big data set, it just takes forever, or I don't know, do some and it will be very inefficient, I would say. And also in bioinformatics, sometimes just similar filter by variance is used. It is where you're interested basically in some genes which are highly variable. And for example, if gene is not like changing, because we have like scientific explanation for that. Sometimes in your sample there are housekeeping genes that are not changing; they just are responsible for various local cells, and they're not changing through the sample, so the transitions or something like this. And that's why we figure that the sample should have variance like to that. So
Okay. That's great information. Yeah, and I may be on a little bit of thin ice because I have not personally like done, all of these experiments and tried to look at visualizations. So take what I say with a grain of salt. I know that TCD is used a lot, and that's why I always say something, because if you just saw how often it has been used, you might think that there's strong consensus. But there are people with very strongly held views who have criticized TCD, and I think part of the issue is that we as humans, like, our visual capability is so powerful that we see patterns in things, right? And then like the ink blot thing or whatever, like we can find patterns when there are no patterns. And so that was kind of the argument, is that basically if you, I'll call it overfit. I don't know if that's really the right word. If you overfit the TC hyperparameters, you just keep changing and changing and changing it, eventually you will see something where you will see a pattern. Okay, that's the risk with TC. So like, yes, if you just like ran TC and you said like, no matter what reasonable hyperparameters I gave it, I got something that seems to show my clusters, you know, between my different types. That's probably a very strong, safe case. But if you like had to twist the knobs a lot until you found the visualization that gave you, you know, what seems like clusters, then beware, you may have just tortured TC to give you something that you're able to recognize. I think that's kind of maybe the way I would put it.
Yeah, I definitely agree. I mean, I used to play with not TCU map a lot, and sometimes when I use very low perplexity, it means that I wanted to see more local patterns in my data. I saw like so many clusters that actually do not probably exist. But if you use like when I use from this perplexity parameter from let's say 20 to 50, which is a recommended range, it was basically very consistent. So I think, yeah, that's important to understand what you are doing, and that you have to sometimes adjust these hyperparameters to see if you can get something consistent, or yeah, if you get some clusters, but like that was only one hyperparameter, you have to be very cautious of that. And of course, it's like for biological setting, other areas could be very different.
Yeah, and can you confirm, my understanding is that UMAP is more expensive, it's slower. And so that's why some people's resistance to switch from TC to UMAP.
I would say so. Actually, it's more following point that it has more speed, it's more fast.
Okay.
It's like improvement. It's basically like when you run with the algorithms on the page, you basically see the same picture. It's just, I don't know, with TC, at least in our, it's not really viable to play with those macro parameters. It's like you can like adjust this complexity, see how it changes, and yeah, there are several great visualization websites running them. So see this in fall, and when you adjust those hyperparameters, you see how like going from the local patterns to global patterns depends on the cost.
Thank you.
Okay.
All right, we'll wrap things here.
Yep. Thanks, everybody. Thanks for coming out, etc. And for those here, feel free to stick around for Kaggle competition stuff, etc. So yeah, thanks everybody.
Thanks again, Liam.